This video is about section 2.2, which covers the basic differentiation rules. We're really doing calculus now because we're taking derivatives. And derivatives, don't forget, are just functions. They're functions that we need to discover, but these functions have tremendous value. The function can tell us the slope of the tangent line to the original function. But don't forget, you got to plug in the x value where you are, where you would like that tangent slope. The first thing I'd like to do is go over the terminology for this new function, the derivative. Now remember, the derivative is a function, so we need to give that function a name. And if f of x is the original function, we already have a name for it. It's f prime. That's the derivative. This is a noun, because nouns are things. Okay? The reason I say that is because we do have other terminology for derivative, but it's a verb, and that's to take the derivative. So this is actually a verb, d dx. This d, I guess you could interpret as take the derivative. D for derivative. Maybe this line here you can think of as the words with respect to x. So the d on top, it's kind of my action, take a derivative with respect to, and why are we saying that? We're reminding ourselves what the independent variable is. Oftentimes it's x, some other times it's t and s and other variables. So I kind of want to remind myself what the independent variable is, and that's how we do that with derivatives. So watch what happens, and this is a verb, action verb. Watch what happens when we take the derivative with respect to x of our function. What you get is a noun. This is a noun, and that is the derivative right there. Now, you know that before we had function notation, remember what we used to call f of x? It was just y. So what you're really doing is you're taking the derivative with respect to x of the y equals function. And this is the more common way we see the derivative written this way. Again, this is a noun. Both of these are. These are the derivatives. Now there's another terminology for the derivative. This is probably the first and last time you're going to see it in this course, and that is a big, huge capital D with respect to x. Of what? Well, of y. And that's just the same as f prime. It is the derivative. This is also a noun. However, we rarely use that in this class. Okay. Now I want to go back for a moment to the definition of the derivative. The definition that we know as of this moment is that f prime can be discovered as a limit process. As delta x goes to 0 of f of x plus delta x minus f of x all over delta x. What this is basically the slope of a secant line. Rise over run. This is the run, delta x, and this is the change in y. This is the slope of the secant line, but it's when we make the 2 points incredibly close to each other that we get the tangent slope. So delta x approaches 0. Now, these are limits. The answer for a limit is not the same as the function value at x, delta x equals 0, because if you did put delta x equals 0 in, look what you get. F of x minus f of x, 0 on top, 0 on the bottom. This is the very reason why we need limits, because by plugging delta x in, we're in the dark. We're getting 0 over 0. We will never get f prime just by plugging delta x equals 0 in. So I want to give you a couple of examples. In the previous video, I had a function that was this function here, x squared. I did go through this entire process, and I learned that f prime, the derivative function, was 2x. And what that implied was that if I drew the x squared curve, I could go wherever I wanted, let's say over here at, right here, at x equals minus 1. I could then draw the tangent line. And just like magic, this function here can tell me the slope. So the slope of the tangent line is not the derivative function. It's the derivative evaluated wherever you happen to be. We happen to be at x equals minus 1. So evaluate the derivative at x equals minus 1. It is minus 2, and that looks about right. It is a negative slope, and if I were to draw it to scale, it would be a negative 2 slope. Let me try one more function. F of x equals 7. If I drew the f of x equals 7 or y equals 7 curve, 1, 2, 3, 4, 5, 6, 7, we know what that looks like. It's a flat line. So what is the slope of any tangent line? We say the slope of the tangent line is also the slope of the curve locally in that area. Well, the slope of this curve everywhere is 0. So the slope of the tangent line has got to be 0. Let's use this formula up here to verify that. Now, f prime better be just 0 for all x's. And let's try it. So limit as delta x approaches 0 of f of x plus delta x, don't plug it in just yet, minus f of x, all over delta x. Okay, let's see what we get on that. The limit as delta x approaches 0. All right, the f of x plus delta x, well, the f of anything is 7, so we don't even care what's in here. It's 7, 7 forever. The f of x is right here, is 7, all over delta x. So the limit becomes 0, and if we plug this in, we get 0. So in that situation, I guess we're not getting much help. That formula is not really allowing me to discover what the offending factor is to divide out. I'm getting this undefined quantity here. It's the indeterminate form. But is it really? 7 minus 7 is 0 over 0. So if that's the case, then maybe we should cross this off and dig a little deeper. But actually something else is going on here. What's going on is you've got this constant here. In other words, I didn't really send delta x to 0 just yet. So it's a little confusing, this particular limit. It's a little bit confusing as to what the answer ought to be. Now, what happens with constant multipliers inside a limit? This 0 has nothing to do with x. It has nothing to do with delta x. It is a constant multiple. It could have very well been 3 or 7 or 2. It is a constant multiplier. It's just the numerator. It has nothing to do with the limit or any of the variables at this point. And what do we do with constant multipliers? With limits, you bring them out front. You bring them out front. Now, when you rip that 0 out, there's a hidden 1 left behind. There's always a hidden 1 left behind. So in reality, this is actually the limit that we want to execute. That's the actual limit we want to execute. However, it doesn't really matter what that limit is. We're multiplying by 0. And so we're going to get 0 as a slope. Now, the tangent slope is 0. That is true. We can see it here. We can evaluate it, although it's a little confusing because you get the indeterminate form, and normally that says dig deeper. But it's because the 0 on top doesn't have anything to do with variables. It's already 0 before we execute the limit. That's the subtle difference with this 0 over 0. So 0 times whatever that ends up being. It could be anything. 0 times something is 0. So the slope is 0, and that gives us this wonderful conclusion. It's called the constant rule. Do we have to use that limit method on a constant function? I don't believe we do. The constant rule says that the derivative of a constant function is 0. Plain and simple. And when we learn this rule, we don't have to use the limit method anymore. And that's when we're really learning calculus. We're building the rules. But we're discovering the rules by running that limit process, because that's the only way we know how to find the derivative right now. But the derivative of any constant curve, y equals 7, y equals 10, y equals 100, doesn't matter. They're all flat. So we can just do that as a conclusion. So therefore, the derivative of the y equals 7 curve all by itself is 0. The derivative of minus 13, that's y equals 13. You would draw that curve, and it's flat everywhere. Even the derivative of 0 is 0. So derivative of a constant all by itself is 0, and we call that the constant rule. Now, earlier we learned that if f of x was x squared, the derivative function was 2x. And again, its job is to simply keep spitting out slopes of tangent lines. You do have to provide it with an x, however. Another way to state this would be d dx. Remember, that is a verb, action verb. The d dx of x squared function, the derivative of x squared, take the derivative of x squared, and you get the noun, the derivative, 2x. So there it is again. But what's the derivative of x cubed? So let's make x cubed our new function. And I don't really know what the derivative of x cubed is without running through the limit process until we learn the rules, of course. Once we learn the rules, then the derivative is actually pretty easy on this function. But let's say we don't know the rules yet. The only way to get this answer is to use the limit method. So f prime, which is what we're discovering, we could say that right here if we wanted to, f prime is equal to the limit as delta x approaches 0 on the f of x plus delta x minus the f of x all over delta x. That particular rule never changes. We can use that over and over again. Okay. We got some work to do here. Remember, never set delta x equal to 0, because you'll get 0 over 0 right away, and that's indeterminate. So what we're going to do here is copy the limit over and over. I need you to be good function evaluators. So f of x plus delta x, what is that? That means wherever you see a letter x in the function, instead put x plus delta x. So that evaluates to be this. F of x is just x cubed. Now I need you to be careful when you have a binomial cubed or any power. Do not just raise this to the cubed power and delta x cubed. There's stuff in the middle. And the way to discover that extra stuff is let's start this problem off by just simply squaring the binomial, and then when we're done with that, multiply it by one more copy. If you remember this process, the hope is that arithmetically a couple things will cancel, plus and minus, and then later the offending factor will divide out. That's the hope anyway. But we have to follow through with the mathematics here. So the first thing I'm going to do is square this binomial. So this will become x squared delta x squared. And what's the middle term? One of each of these. So it's 2x delta x. That, unfortunately, needs to get multiplied by x plus delta x. And yes, there's a lot of multiplication that has to be done here. Let's do it extra carefully. It's going to get messy, guys, but it'll clean up. All right, we got to multiply these together. First times first here is x cubed. X squared reaches out, distributive law, times delta x. Be careful, write it all down. Plus, the 2x delta x multiplies with an x. The 2x delta x multiplies with a delta x squared. Sorry, a delta x. I get delta x squared, right? 2x delta x delta x. Got it. Last but not least, delta x squared gets multiplied by the letter x. And delta x squared gets multiplied by a delta x. Oh, and don't forget, minus x cubed. Thankfully, I have some room for that. Wow, look at all that multiplication we had to do. Now, I promised you something, and that was that arithmetically something better cancel. Here it is, x cubed and x cubed. Good news, that's gone. The second thing is, let's combine our like terms together to see what we have. This is 2x squared delta x. There's 1x squared. You got 3 of them. This is 2x delta x squared plus 1x delta x squared. You've got 3 of those also. And what about this delta x cubed? A lot of work. Now the next step is factor out the common factor. We hope it's the offending factor. So the limit as delta x approaches 0, delta x is the common factor. Out it comes. And there it is, guys. Now, why do we keep getting 0 over 0 on these problems? Here it is, because of this offending factor. And now it's gone. The final limit we need to execute, we can use direct substitution and expect to get a result. And this is what you're going to get. Delta x goes to 0 here, and you get the limit is 3x squared. All right. I really used the limit method on that, and we got ourselves a result. So let me summarize some results for you. The f of x was x squared. F prime ended up being 2x. The f of x was x cubed. F prime ended up being 3x squared. And I will say, if I kept going, the f of x could be x to the 4th power. F prime, well, think about what it might be. Follow the pattern here. 2, 3, 4, x to the 1, 2, 3. So this is what happened. Mathematically, people went through this. They used the limit method because that's all they had. And they went through it with these power functions, and they saw the pattern. And I think you see the pattern as well. This means that we don't need to necessarily use the limit method for such a function. If f of x is just x raised to a power, then f prime is equal to the following. It looks like the power comes down and parks itself out front, and we deduct 1 from that power. And that really matches what's going on up here. That means that if I had a new function g of x and it was x to the 100th power, can you imagine taking x plus delta x and trying to raise that to the 100th power? It's not impossible, but there's a lot of room for error, so we wouldn't want to do that. In fact, after all of that work that would take such a long time, we would discover this. So right now we have 2 very valuable rules. The valuable rules are that, number 1, the derivative of a constant is 0. Number 2, the derivative of a power function. You take the power down out front, and you deduct 1 from the power. Now the next rule I want to show you is called the constant multiple rule. Now, I kind of cheated a little bit on this one because I used the constant multiple rule to help us discover the constant rule where it was equal to 0. So what I'm going to show you here is, let me see if I can just deliver a pretty nice looking proof for the constant multiple rule. Let's say, for example, we had a function g of x. And all it was some constant multiplied by some other well-known function, f of x. Now, if you've got a function f of x, we're going to assume that maybe you were able to get the derivative of it at some point. So f of x may be a function whose derivative you'll be able to discover. But what's the derivative of a constant times f of x? Now here's a good question. Because of this constant, do we get 0 times f prime, which would be 0? And that is not the case. Guys, let's discover g prime. Let's use the limit method, because it should reveal something to us. The limit method says do g of x plus delta x minus g of x all over delta x. That's the limit method for finding a derivative. We don't need to know any rules to use this method. They're all built in. So what is the g of x plus delta x? Well, put x plus delta x in here, which means you put x plus delta x in there, and you end up getting c times the f of x plus delta x. Let's put x into my g function. So put x over here because they're the same. You get c times the f of x all over delta x. Well, take a close look and you see that there is a nice common multiple of c. So the c comes out front and we get f of x plus delta x minus the f of x. And let's not forget we're dividing by delta x. Now, this c, this constant multiplier, is not affected by this limit. Because delta x is going to 0, delta x can be anything, and c will never be touched. So when you have a constant multiple in front of a limit like that, you can just pull it out front. I think we did that with limits before. So a constant multiplier, when it comes to limits, is unaffected by the limit itself and can just be parked out front for later. So we'll park it out front. And it says, you know what, if you can evaluate just this limit, then maybe that'll help. And then when you're done with that, then actually multiply by the constant. Well, I think you can evaluate this limit, because we know what that is. That's f prime. So that gives us the constant multiple rule. The constant multiple rule says the derivative of any constant that is multiplied, not added or subtracted, but multiplied by a function is simply the constant can come out front, save it for later, and just take the derivative of the function itself. So the answer is not 0. It's c times f prime in that case. So that is a nice rule to remember. It's called the constant multiple rule. Now I'm going to finish up with the sum and difference rules. And it turns out that these are called the sum and difference rules. And it turns out that the derivative, ddx verb, of two functions that are either added or subtracted together, like that, not multiplied, but added or subtracted, think of it as a distributive law for our derivative. Basically, you take the derivative of the f function all by itself, and then you plus or minus the derivative of the g function all by itself. So it actually makes things quite easy. It's simply f prime plus or minus g prime. What that says is that derivatives work very, very well with addition or subtraction. You just do each term separately. I will tell you that that is not the case for multiplication or division, and we'll get into that a little bit later. Let's use all these rules. I've got a function, and that function looks like this. And I would like a derivative. So let's throw the function right in the mix, and let's do the derivative. Now remember, I can do this term by term. They don't interact with each other. You do each one separately. So you can start off by separating and actually do 3 different derivatives here. Do this one, and finish up with this one. That's the beauty of pluses and minuses. Now what's this? Constant multiple. What's that? constant multiple. What do we do with constant multiples? Just like limits, they come out front and they just sit out there and they wait for you to take the derivative of the root function. In this case, it's just x squared. The 3 will come out front and wait for you to take the derivative of the root function, which is just x, and then minus, we've got one derivative to deal with over there. But that is a lone constant. Pretty lonely 7 back there. So let's do this. Constant multiple 4's got nowhere to go. It sits out front, but we know the derivative of x squared. That's a power function. The 2 comes down, and we deduct 1 from the exponent, and that's what we should have. Now the 3 is going to sit out front. It has nowhere to go. We've never done this one, have we? The derivative of x to the 1 power. Let's use the power rule. The 1 is the exponent. Now deduct 1 from that exponent. But x to the 0 power is 1, isn't it? And over here you got the derivative of a constant, so you know what that is. Derivative of a lonely constant is 0. So the derivative becomes 8x plus 3. And that's the derivative of that function. Now that brings up an interesting point that I'd like to look at, and that's this. What's the derivative of x? One way to look at it is to do what we just did there. Use the power rule. It is x to a power after all. The 1 comes down, deduct 1 from that exponent, but that's equal to 1. 1 times 1 is, no, the answer is the derivative of x is simply 1. But here's another way to look at it. That's dx over dx. Now I realize that the derivative is not really a fraction, but it looks like a fraction. In fact, it looks like same over same. And here's another way to look at it. mx plus b. I think we remember what this is. This is a line with a slope everywhere of 1. So it's a good way to look at the derivative of x. Okay, we're not finished with section 2.2. There's more to talk about, but I do want you to go through and start taking the derivatives of some of these functions. Most of them will be polynomials, for example. But I'm going to follow up with another video, and the other video will talk about what the slope of a graph is. Slope of a graph, really locally on the graph, it's the slope of the tangent line at that point. I'm going to find the full equation of a tangent line. We've been talking about finding just the slope, but I want the full equation. And we should be able to do that algebraically. If I have a slope and a point, that's good enough to find that equation of the line. I'm also going to look at the derivative of 2 trig functions, sine and cosine. We'll see what the derivative function of those are. And finally, I want to talk about why we even do this. What's important about a derivative? You can calculate the average rate of change, the average speed, without using calculus. That's just, for instance, distance divided by time. It's one number. But finding your instantaneous speed requires calculus, and the reason is because your instantaneous speed actually is the slope of the tangent line. And so calculus will reveal that. So we'll pick that up in the next video. Thank you.